X is finite dimensional, is the screen visible?
Yes, sir.
Okay, so this is if and only if the closed unit ball is compact. So one way is that if it is finite dimensional, then it is compact. That is the easier one. So if dimension of X is n, then X is isomorphic to L1 of n and since this
Hello.
maybe let me write so over therefore. So let's call the from isomorphism. So
Sir, your voice is breaking.
uh, then this is okay. I don't know, today there is a lot of connection in them. So okay, so if we have so, so is not
Sir, what you write is not visible.
showing what I am writing. It seems to be frozen. So yeah, so what I am saying is that in X, try to again say it. I don't know. There seems to be some problem. So let's see if it works. So I'll just say anyway. This will be visible to you later. So we have T of this ball is compact, and this will imply that B, which is equal to T inverse of TB, this is compact. Right, because we know that this T is an isomorphism, so it is continuous, and T inverse is also continuous. So that
So
is one
actually,
part.
we missed the audio part also for last 3-4 minutes. Like after you mentioned that X is isomorphic to L1, and then wasn't audible also, and the screen also didn't change after that.
Okay. So what I said is that we know that X is isomorphic to L1N, which means that there is 1 onto linear map T such that T is continuous and T inverse is also continuous, right? From X to L1 of N. So now if I take the closed unit ball, then its image, so because B is closed and T inverse are both T inverse is continuous, so therefore T of B will be closed, and the, because B is bounded, then T of B is also bounded. So T of B will be closed bounded subset of L1 and L1N, and therefore it is compact. Okay, I think now it should be visible. Is it?
Uh, Now actually it is completely
Yes.
Okay, in my other screen it is showing, so it should be showing soon. So T of B is compact and B is equal to T inverse of TB. So therefore, that is also compact. Right? So, so that is one part. The screen visible now?
yeah, I'm unable to see. Like I can't see the screen.
Yes, sir, it is visible.
Okay.
I don't know what is. So okay, let me try to do. Anyway, this PDF will be available. Today we have lost also a lot of time, but we'll try to make it up. So okay, so let's first then the closed unit ball is compact, and then we have to do so that if the closed unit ball is compact, then we have to show that it is finite dimensional. So suppose B equal to X in X such that norm X less than equal to 1 is compact. Then we have to show that this X is finite dimensional. So first of all, because B is compact, if I take any open cover of B, then it will have finite subcover. Right? So since this is compact, this implies that there exists a natural number n and points xi in B such that B is contained in union of Bxi half I equal to 1 to n. Right. So where this is the I think we use other notation. So instead of B for the open ball, we used D, right? Because we are using B for the closed ball. So I think we used where this is x in x is that norm of x minus xi is strictly less than half. So why is this true? Because if we take uh, open balls of radius half at all the points of B, then that forms an open cover of B. And because it is compact, it will have finite subcover. So there will exist finitely many these points such that the open balls, the union will contain this B. So now what we will show is that now we have got finitely many points x1, x2, xn. So we will show that uh, x is actually span of these x1, x2, xn. So let W equal to span of x1, x2 up to xn. So claim is that V is same as W, which implies the dimension of V is less than or equal to n. Right. So if because W is a finite dimensional subspace, we are taking only finitely many vectors and its span. So dimension of W is less than equal to n. If I show that W is same as the not V, we are writing X. The dimension of X is equal to dimension of W, so it is less than or equal to n. So we show this. So we will prove by contradiction. So suppose W is a proper subspace, then we will use Ree's lemma and get a contradiction. So since say WO is finite dimensional, it is a closed subspace of X. So if W is not equal to V, then W is a proper closed subspace of the nonlinear space X. So by the Ree's lemma, there exists U in X such that norm of U is equal to 1 and distance between U to W is greater than equal to 3. Right, so we are taking epsilon equal to 1 by 3. We know that for every epsilon positive, there will exist a vector such that the distance is bigger than equal to 1 minus epsilon. So if I take epsilon equal to 1 by 3, then we get that distance of u to w is bigger than equal to 2 by 3. So distance of u is equal to 4. So we know that because the distance of u to w is the infimum of all the distance from this vectors. So therefore, we get this. But this will imply that this will be a contradiction, because what we have seen is that this B is a subset of the union of these open balls of radius half centered at xi. But here we got u. So since norm of u is equal to 1, u belongs to B. But u belongs to B, and B is a subset of union of d xi half. This implies there exists some xi such that this u should belongs to d of xi half, but this will imply that distance between u and xi, this is less than half, which is a contradiction. To let's call this star. Right. So the conclusion is that this W cannot be a problem. So hence W is equal to X. Is this clear? So Ree's lemma was the crucial thing that is needed to prove this theorem. And for some particular example, so this shows that for any infinite dimensional non-linear space, its unit ball is not compact. But some particular example, you can directly also show that it is not compact. For example, if you take say any sequence space LP, for example L2 if you take, then if you want to show that the closed unit ball is not compact, you just look at the standard vectors E1, E2, En, E1, E2, E3 and so on, where Ei is at the ith place you have 1 and all the other places are 0. Then if you look at the distance between any two of these, Ei and Ej, then that is a fixed constant, right? For L2 space, it will be root 2. For LP space, it will be 2 to the power 1 by P, right? So, or you get a constant. So you get an infinite set such that distance between any two points is a fixed positive constant. So this will imply that that infinite set cannot have any convergent subsequence. So therefore it cannot be compact, because in metric space we know that if a set is compact, then every infinite set will have the convergent subsequence. So okay, so for particular example, you can give a direct proof also. So next, let me see how much time I have. Okay, next let me talk about quotient space. So let V be a nonlinear space and W be a closed subspace of V. So then we have this V mod W. So for a vector space, you might have seen that if you have any vector space and any subspace, then you can define the quotient space V mod W. So how is the quotient space defined? That is by defining an equivalence relation. So we define an equivalence relation on V by X is related to Y if X minus Y belongs to W. So this is the standard thing that for any vector space, so you can define this equivalence relation. Then you can check that this is an equivalence relation. So then for any X, this is the equivalence class containing X. So which is nothing but all the vector Y in V such that X minus Y belongs to W, and this is same as X plus W, right? So if you take x plus a vector in W, then that is exactly the equivalence class. So these are called the cosets. So this is coset of x, and then we have the quotient space x quotient y. This is the collection of all this for x in x. So this is called quotient space. And you can define a vector space structure on this. So x mod y is a vector space with the operations. If I take x1 plus x2, this is the coset of x1 plus x2, and alpha times x is equal to alpha x. So I mean, it is easy to check that these are well-defined operations, and then with respect to this addition and scalar multiplication, this will become a vector space. So x mod y is a vector space. Now, here what we were taking that this is actually v and w. Okay, so we have this is a vector space, but we also want to define a norm on this. So how do we define the norm? So on the vector space v mod w, we can define a norm as follows. So if we have to define norm of any vector in this. So any vector in this is the norm of x. This x, instead of this, you can simply write x plus w. So norm of the coset x plus w. How do we define this? So this is nothing but the infimum of norm of x plus w for w belonging to capital W. Right? So you look at the infimum of for all the vectors in this coset, and that we are defining the norm of this coset. So this is the norm defined on the quotient space V mod W. So this is the
Will it be
definition.
same as dxw also?
Sorry?
Will it be same as dxw? You had defined a notion of distance between point and a subspace also. Now the infimum.
Right. So yeah, so this is same as the distance of x to the subspace W, right?
Because like plus w and minus w can be interchanged.
Exactly.
W
So this you can also see just the distance of the point x from the subspace W. So now what you will see that this will be a norm if I assume that W is a closed subspace. Closed because otherwise, if this suppose this is equal to 0, norm of a coset is 0, so that says that infimum of norm x plus W is equal to 0. So that will imply that x will belongs to the W closer, right? Distance of x to W is 0. So x belongs to W closer. So x need not be in W. So x plus W, this can be different from the zero vector. Zero vector is just W, right? So, but if I assume that W is closed subspace, then this is equal to 0 will imply that this equivalence class of x, this is the zero vector. So so again, you can check that this is well defined. So because for this coset, I can take different representation. So suppose you take instead of this x plus W is suppose equal to x prime plus W, then that will mean that x minus x prime belongs to W. So let me just say that, check that. The above is well defined. So whenever we deal with coset, you need to check that this is well defined. So that is easy just by the definition. And then the main result is that this will be a norm. So theorem let V be a norm linear space and W be a closed subspace of V, then this norm defined on V mod W as above is a norm on V mod W. So this V mod W, it's a norm linear. So V mod W, this quotient space, is also a norm linear space. And if V is a Banach space, if V is a Banach space, then so is V mod W. So if you assume that V is a complete nonlinear space, then the quotient space is also complete. So I have overshot the time, so let me stop here. So this, I mean, you can try to prove this theorem yourself also. Once you have defined it, it's just verifying the things. So maybe the completeness part at least I'll show next time. So this is this theorem actually gives you new norm linear space. So if you have any norm linear space, then you can form many more norm linear space by taking the quotient space with any closed subspace of V. So that is a general thing that you can construct more non-linear spaces from a given non-linear space. One more thing that we'll do a general result is that if we have a non-linear space which is not complete, so we are seeing that if V is a complete nonlinear space, that is something important, because we'll see later that many of the theorems hold true for Banach space if I assume that this nonlinear space is complete. So suppose I have a nonlinear space which is not complete, then there is something called completion of that. So, I'll discuss about if you have seen for any matrix what is known as complete space, then on also on that, and after that about more on the dual of a space. So on bond we'll see the theorems of functional analysis. There are some very important theorems, so we'll prove those things. So let me stop